Okay, I'm sorry, it's a minute past time to get started. Little problems with our technology, like this recording program didn't work to start here. But I think everything's going. One statement before we get started. On the homework problem 2, it's the problem with the failed ballistic pendulum experiment. I had students ask me about it, and so I did it in the class this morning, the Physics 251 class. So if you want to see and hear the solution, just go to the YouTube videos for Physics 251, and the first 15 or 20 minutes of today's lecture is the solution to that problem. Things that we learned as we did it is its wording is a little bit confusing. It says that treat it as an inelastic collision. And now I told you in class that inelastic means it's just not kinetic energy conserved. But when we use inelastic, we're going to mean completely stick together. Well, that's not what this problem means in inelastic. It just means that kinetic energy is not conserved in the collision. So in essence, just ignore that statement about inelastic. It's not an elastic collision. You have to calculate the energy that the swinging pendulum has and the energy that the bullet had to begin with, and use conservation of momentum and use all of that to solve it. So you can see the solution there on the YouTube videos to go over. Now for today's lab, any questions on how to get to the YouTube videos for all of our lectures? Everybody's down with that? Okay, today's lab is about collisions. Now I already showed you exactly what we're doing in lab on class last Friday. So I don't have things set up here to go over it again because you've already seen it once. But what I will do is just go over the theory and what's going on. So for starters, we're going to have collisions, and collisions will have momentum conserved by Newton's second law if these two things, one of them or both of them, are zero. You go, oh yeah, hey, look at that. Once again, I was so worried about all the technology problems. You guys should see how bad the video is now, but at least it's in focus. It's just grainy focus. So imagine that you can see Newton's second law right now. You will in a moment. Newton's second law tells us that if the net force acting on my system is zero, or the delta t, the time, is zero, then I'll have momentum conserved. So in our collision case, our collisions are going to be very short, and the only external force will be the force of friction. Now, there is friction on these tracks. One word of caution. Before you start, take your carts, spin all 4 tires. Tires, wheels, you know what I mean. If you have one that stops quickly, take it to Yafet and say, okay, this one has a bad wheel. These wheels go bad. I don't know why. So we'll trade it out so you don't have that, because that will put a lot more friction in if you have one where the wheels don't spin. Don't have to do it right now necessarily. But I told Yafet not to spend his time checking every single one because it's a lot faster to have you guys do it. It takes you, a total of 20 seconds where it takes them a total of 20 seconds times all the stations. Okay, getting back to this then. We should have, by theory, momentum conserved if the force of friction is zero or the time for the collisions is zero. Is the time for the collisions absolutely zero? No. Is the friction absolutely zero? No. So that means it's not going to be perfectly conserved. It will be close to conserved because the time is very short and the force of friction is very small. So you put those two very smalls together, and it's a very small change in momentum, but there will be change in momentum. So when you're doing your evaluations on if momentum is conserved, you're going to say if momentum was conserved, considering that there is that slight friction, so taking that into account. So don't say, no, technically momentum wasn't conserved because there was friction. We know about that friction. It's a small thing, so we're looking for things like, was the slope continuous, or did it have a discontinuous change? That's the type of thing we're looking at. So the slope would keep in mind that there is some friction. These two equations are not shown in your lab guide. Those are the equations you're actually using in the lab today. You're not doing any calculations. So you don't have to have examples of using the equations today, but those are the actual equations we're using. That momentum is mass times velocity. Notice it's just a scalar here because we're doing one-dimensional collisions. And kinetic energy is 1/2 mv squared. This second form for moment or for kinetic energy is very useful, especially when you're looking at collisions. Since momentum is mass times the speed, well, mass times velocity for vector, then you can just solve that for the velocity, the speed, momentum over mass, and so that means kinetic energy is 1/2 mass times momentum over mass squared, or 1/2 mass times momentum squared over mass squared. Well, you cancel one mass, and you have kinetic energy is p squared over 2m, this form here. So it's convenient to be able to relate directly momentum and kinetic energy. So let's go straight to what you're doing in the experiment. First, your scientific method. Now, this here is different than what you see in a few ways. I went over and re-edited the lab in preparation, and there are some things I'm holding to you to and some I'm not. So one thing I'm holding you to is I want you to have at least 3 trials in your testing of your hypothesis. Right? It takes virtually no time to do a trial. I want to see at least 3 with different situations. So, maybe this one's going at roughly twice the speed of that one, then that one's going roughly twice the speed of this one, then they're going roughly the same speeds, or, changing up the situation so you can see if your prediction is correct under a few different situations. So make sure you have at least 3 tests of your hypothesis. Your hypothesis, you need to start with an observation of something you see that's a one-dimensional collision. So one-dimensional collision means it's all in a straight line. I don't want you worrying about, okay, so, playing pool, I have the ball set there and it's a 90-degree angle between where I want the ball to go and where the other hole is. Can I make this without scratching? The answer is, if there was no friction, no. But I don't want you to be worried about those angles, just things that are in a straight line. So your observation should be things that are in a straight line. So, I don't know, I guess it was last school year, we were out playing football, and all of a sudden we hear something, look up, and there at the stoplight, there's a car stopped, and another one that's skidding behind it and hits it. That'd be a perfect example of, hey, I saw a collision, 2 automobiles. Then your hypothesis needs to explain about what happened to the velocities, with talking about what we've learned with collisions. And then you need to test predictions of your hypothesis with your experiments here. I know I was talking to Brady before class. I didn't say this to him because I hadn't thought it through. I want your test to not be this required stuff here, but to be additional to that. You're required to put 2 carts on the track, have them hit each other with an inelastic collision, and record the momenta and kinetic energies of each cart before and after. So total 4 measurements. When you're doing your collisions, remember when I did them in class? Say, yes, I remember. Yes, thank you. Okay, so when we did these in class, we had, a big selection of data. And I zoomed in, so I was only looking at about 3 data points before the collision and 3 data points after the collision. You need to be careful that you can correctly identify where the collision is. If you're not identifying where the collision is, clearly any measurements you make are going to be wrong. Second, zoom in so you're just seeing about 3 data points before and 3 data points after, because the friction aspects are going to look much bigger if you're looking at a big range than if you're looking at just before to just after. And so just like when we did the car collision problem, in class yesterday, I had the initial speed of car 2 that I had to calculate. That wasn't the same as the speed just before the collision. Why? Because of the friction. So we have that same effect, but we aren't looking at the friction as a significant thing. We're just looking at the collision. So make sure you zoom in on that. To get the actual values, you're going to have something like, okay, here's cart 1 before the collision, cart 2 before the collision. At the collision, they're going to do something like, and I'm just going to, it's not going to look like that, but I'm drawing something. So you want to zoom in, so you just have about 3 data points from before the collision and about 3 from after. Obviously, there's going to be some in between as well, but it's the before and after that we're comparing. And so then you use the data select tool, which is, really? I had it running in the background. Apparently, I killed it. I had this all ready beforehand, and then I ran into problems, and apparently I killed this in trying to fix the problems. Don't worry, it'll come up. Okay, I tell you don't worry mostly because I'm worried. Where's recent? Okay, so here's your no data, not connected, so I'm not going to take any data. But this tool right there, see the hand pointing to the tool? That's the tool that you use to make a data selection box. And then you can resize that box so it's only going to have the 3 data points and drag it over the data points you want. And then this sigma, if you click on that, it turns on and off statistics. Click on the arrow and you see mean is the one that's going to show. So as long as it's turned on and you have that data selection box, it will show you the average, the mean, of the data that's inside the box. So you just turn on the box. You're going to have to turn on the box once for the momentum graph and once for the kinetic energy graph. It won't be the same box for both. Drag it over, read the information, make sure you write it in your lab report. You'll also have, you always have to have uncertainty with measurements, right? So how do you get the uncertainty? Just go back here, click the down arrow, and don't just show the mean, show the standard deviation. That standard deviation is your uncertainty for our purposes. So you can get the standard deviation and the mean there, and so you have both the value and the uncertainty. Note your units are in kilogram meters per second for momentum and joules for kinetic energy, so those are the units you're using. So that's how you get the before and after. It won't take long. Put the box on, resize it, drag it to this one before, this one before, this one after, write the numbers down for each one. While I'm here, another thing that you need to do is to enter, you're going to have to measure the mass of each one of your carts plus the mass of this black bar. They're all nominally 500 grams. I think the black bar should be pretty accurate to 500 grams. The carts are probably plus or minus 5 grams. So you're actually going to measure the masses of all of these. Now, just to make sure we're all clear, when I use the triple beam balance, what's the first thing I do when I start? Zero it, right. Remember that, zeroing it. Don't trust the person before you. Make sure it's actually zero. Then I put this on. The triple beam balance measures out to tenths of a gram. So when I make my measurement, what is my precision for the measurement? To hundredths, because I estimate one beyond what it can measure. So your mass measurement had better be out to hundredths of a gram, not out to tenths of a gram. And then how do you determine your uncertainty for this?
Plus or minus 300.
Okay. Jonathan says plus or minus 300. I didn't hear what you said. Plus or minus 300. Where did that come from?
You told us that.
I told you that. That is one way. The uncertainty is an estimate of how much error you think you might have had. Now, you'd better be good to well less than 1/10, right? It's very easy to tell the difference in a tenth of a gram on that balance. And so I estimate that, well, I know really well that I'm going to be plus or minus a quarter, right? I'm going to definitely be within a quarter of the separation. And so I round that to 0.03. You might be a little more optimistic than me and say plus or minus 0.02. That's fine. Plus or minus 0.05, you should be better than. If you go bigger than 0.05, you're going to lose points because that's not a reasonable uncertainty. Right? That goes back to our first lab on estimating uncertainties. Okay, another thing on this is how do you enter the masses? Once you've measured the mass of everything, you're going to put the carts on. It says to label the carts cart 1 and cart 2. And how do you know which one's cart 1 and cart 2? The answer is not super intuitive. One of these will be channel A, and one will be channel B. And cart 1 is the one closest to channel A. That's what determines which one's cart 1 when you're doing your experiment. So when you label them, this is cart 1, this is cart 2, make sure the one that is labeled cart 1 is the one closest to the sensor that you have plugged into. Are they labeled A, B, C? 1, 2, 3. The one that's plugged into 1, and then you have it matched up. You need to put the masses of the carts into the computer because it's doing the calculations for you. It has to have the right number for mass. So to do that, you click on calculator. You have all the variables. So for mass 1, I put in a number here. And so notice the units are kilograms. Your carts are nominally 500 grams, half a kilogram. So I'm going to put in 0.5, and let's say mine was 0.50435. So there's my mass in kilograms. Make sure I hit enter. Mass 2, let's say this one was 0.50222. So I put the masses in. Please don't mess with the other equations or you'll mess up your entire experiment. Right? That's not the goal. If you want to check and see that you have those right, if you go to data summary, it will show you the equations that are being used to calculate the momenta and the kinetic energies. And then down here, it shows the constants, so you can see the numbers that you entered for the masses. It's kind of useful. That is when you go to data summary and it's on the calculator. If you're in data summary and you have the first one, it shows you what's measured. All those little warning signs are because I'm not connected to anything. Okay, getting back to the experiment then. That's the right one. So for the experiment, the instructions say to put the Velcro sides together so they're going to stick together. And before you do the experiment, please do this before, because it loses its value to you in the learning if you don't do it until after. If you do it after, you already know the answer and you're just sketching what you know. I want you to think about what's going to happen when you do this. Are you going to have momentum conserved and why? Are you going to have kinetic energy conserved and why? Right, so I want you to answer those questions and to sketch. Notice it's about a 3-inch square graph, something that's like that. Sketch what you think the momentum and kinetic energy graphs are going to look like. Now, these don't need to be perfect, and they only need to show this much data. Right? Nobody cares what's happening from the time before you push the cart until the collision occurs. All we care about is basically from a second before the collision to a second after the collision. Actually less than a second before to less than a second after, just like 3 data points before to 3 after. So that's all you need to have, all you should have in those diagrams, is what you expect to happen from just before the collision through the collision to just after. And so you have both what it looks like, what you think is going to be going on in terms of conserved versus non-conserved quantities, and your reasons. Then you actually do the experiment. Make them come. They have to be going slow enough that they stick together. So you can't go, whee, and just have them crash off each other hard because they won't stick together. And then you answer a couple more questions. Then you go on to testing your predictions of your hypothesis. Now I want to add encouragement. This is not required, but I strongly encourage you to play around with elastic as well as inelastic collisions. Try different situations so you can see how these things work, right? Physics is about figuring out how things work and understanding, and that curiosity of what will happen if I do this is one of the things that I want to encourage you to do. I changed it for next year that they have to do an elastic as well as the inelastic, just to make sure that they look at both ways. But please take a few minutes to try some experiments of different situations to see how they play out, even if they're not part of your official lab report. Okay, any questions about the process? Yes?
Does it matter which end of our track is left and right?
No.
Okay.
The reason for that is so you can have a positive line. But if you go the other direction, you just have a negative line. So it's not really an important thing. Any other questions? One question that Yafet asked me was, why are you looking at the data for cart 1 in the very first question? Cart 1 and cart 2 should be exactly on top of each other. The first question has you just put the cart on here and push it and let it go all the way across. The reason for that is so we can make sure that both detectors see the cart all the way across the track. That's the point of doing that. And then it asks you if the line is constant, if it should be, etc. So the keys for that are making sure that your detectors see the carts all the way across the track so you don't have places where it won't be taking data. And then to note the effects, how close to ideal these tracks are or are not. Any other questions? All right, and we will be back to groups of 2 again today. So you go ahead and get started.